Swayam Prabha. Digital India. Educated India.
Hello and welcome to session 15 of our course on quality control and improvement using MINITAB. So, I am Professor Indrajit Mukherjee from Shailesh Mehta School of Management, IIT Bombay. So, last time what we are doing is that we are discussing about process capabilities, and in case it is non-normal, what is to be done. So, some data sets we are just exploring and trying to see, and I told also there are two types of transformation that is available. One is Box-Cox transformation, which is a lambda transformation, optimal lambda transformation that we are doing. So, if the CTQ is y represented as y, so y to the power lambda, what should be the lambda values, and that will transform the data into normality, and then we can analyze process capability like that. Okay, and the specification will also be transferred like that. So, some examples we have taken, and we will try to extend that lecture to some extent and try to see that how for the previous data what we have taken, how this transformation works in capability analysis when there is subgroup size is involved into that. Okay. So, so this is what we have done. So, I will go to the examples like that. So, I will go to the examples, and so this was the ring data that we are using samples. So, these are the subgroups that we are having. So, what we did is that we went to stat and then quality tools, and then we went to capability analysis, and there is a capability analysis 6 pack also over here which we can use in case transformation is needed. So, I will go to normal over here, and then in the subgroups I will mention that these are the subgroup informations that we are having, and let us select this one. And lower specification, what last time also we have seen, is 73.965, and the upper specification was 74.035. And then we went to transformation, and we said that in case transformation is required, use Box-Cox transformation over here, and I click OK, and then in test what I do, 1 point going outside, that will be the control that we are using over here, stability criteria, and then we write that if it is more than one subgroup. So, I use R bar concept, R bar by D2 concept to calculate the standard deviation, and based on that we will calculate capabilities short term. Okay. So, in options we have not mentioned any targets over here, we can write 74 as the target like that. Okay. Capability and benchmark, what is sigma levels that we have discussed last time. So, in case you want to check the sigma level, you can do that. So, if I click OK over here, what happens is that this analysis comes up, and what you see over here is that capability analysis over here and USL and LSL are transformed over here, target is also transformed, the values you can see are different because the MINITAB software used a lambda transformation of 5, and after lambda transformation what happens is that you can see this Anderson-Darling test over here, and p value is more than 0.05, that means it adheres to the normality assumption over here, and X bar charts are shown over here on transform data, and range is also shown over here on the transform data like that. And this is the overall capability analysis, and CP calculation what you can see is 1.17 and that it is saying CPK is about 1.13. The CP value is not changing much. So, I think transformation after transformation also the data seems to be more or less and very close to normality. So, in this case we may not have used transformation because it works well. I am telling you that even if some small deviation, moderate deviation, capability analysis is not much impacted like that. Okay. But if it is very skewed, in that case we have to think like surface finish, what we have seen like that, and surface finish are generally skewed dimensions like that. Okay. So, those things needs to be, those CTQs needs to be converted, and then according to target we can see the process capability analysis. So, PP and PPK, CPK values are given over here, and those information you can get, and PPM levels are also given. So, total PPM within and overall, that is also given at the end. Okay. So, in the graph you will get all observations and also the randomness of the observation last 25 subgroups. So, these are the observations and it shows scattered towards and there is no such pattern what is revealed over here. So, in this case we can consider that this analysis is quite perfect, but CPK value indicates that we need to improve. If we have to improve beyond 1.33, so that is the thing we need to ensure. Okay. So, let us take another example over here. So, we will close this one and we will take the container example where lower specification is given as 200. So, in this case I will use another transformation. So, quality tools maybe capability 6 pack I will go and normality analysis we are doing, and container 1 to container 5 over here, and I select those observations, and then lower specification is 200 what was mentioned last time also, this will be blank. Transformation, let us go for Johnson's transformation now and click OK, and then we test this one point going outside, and then estimation over here, the same estimation process we will follow, and in options target value is 74 we can delete, and otherwise capability analysis we want to see. Okay, one sided, so CP values will not come. So, in this case anyhow, so we have changed this data set, we have given options for transformation as Johnson's transformation over here, and we want to see what happens. Okay. So, when you click this diagram over here, what you see is that it has used is family of transformations. So, in this case what happens is that this is the transformation that is done on the y characteristics, you can see x. So, x will be replaced, let us say, by y. You can think about the data that is given is y information, or CTQs generally we expressed like effect, that is the CTQ. So, final outcomes that is the CTQ and that is y. So, MINITAB says that we have transformed with a symbol x like that, the data set is x over here. Okay. So, then what you see is that after transformation of the data set 0.033, so y is transformed to 0.033 plus this with the function, and then x minus this, and this is the family of transformation that is used to calculate the parameters over here. Parameters are calculated, and then the final outcomes what you see. So, data was transformed, and why it has done transformation, because the data does not follow normal distribution. So, how do we ensure that one, that we will see. And after transformation what happens, the p value over here, what you see, Anderson-Darling test p value is more than 0.05, and I told that if it is more than 0.5, we have not explained on that aspects, we will do next time in our subsequent lectures, and we will try to see what is the p value, but at present we assume that if p is more than 0.05, in that case it adheres to normality like that. So, the data set was plotted and p value was calculated as 0.729, and that adheres to our normality assumption. So, there is no problem with normality after transformation like that, and the index was calculated over here, PPK index was calculated as 0.61 like that. Okay. So, this is already given over here. So, this is what I wanted to show over here, and this is the transform data on which the analysis was done. So, I will click this one. Now, this data set is in subgroups. So, how to ensure that this is normality? So, what I did is that I took all the data set into one column C16, and then I went to stat, basic stat, and I wanted to check normality assumption over here. I gave container data all, and in this case I wanted to do Anderson-Darling test, and I click OK, and what I found is that p value that I am getting is less than 0.05. So, less than 0.05, and that indicates that data is non-normal scenario exists over here. So, non-normality is there, that is why Box-Cox or Johnson's transformation are used, but both the transformation will work everywhere, it does not you cannot ensure that one. Sometimes it works and sometimes both can fail also. So, that is also possible like that. So, in case everything fails, then we have to see some other ways to calculate non-normal process capability. So, there are fitting distribution, and based on that you will get options in MINITAB to do that. Okay. So, this is the data set that we are talking about over here, and then go to the slides what we wanted to cover next. So, this is about process capability. Now, in case of attribute data, where we have defects or defectives like that, so in this case how do we calculate the sigma labels or process capability, that way, is there any conversion that we can do? Okay. So, So, for continuous data we have seen that earlier method works well, and in case of process using count data, that is defects over here, some other units are used over here, defects per units, defects per million opportunity, and then based on that we can signify, we can tell what is the sigma level like that. Although normal distribution assumption is taken to convert this one. So, but basic assumption is that we can make a sigma level transformation from the defects per units, defect per opportunities, and from there we can calculate the sigma, we can go back to sigma level, and based on that we can also calculate process capability like that. So, there is a interrelationship between all these metrics that we are using. Okay. But we are assuming over here process stability, that is the basic assumptions that we are adhering, and customer, let us say, specification given as sigma level should be greater than 4 or something like that in this particular case. But last month what happened is that I have manufactured 16,000 approximately units, and over a period of 18 days, and I want to check what is the sigma level of the process, and we found out that 231 defectives were reported like that, or we can say defects or something like that. So, you have to define. So, let us say it is defects over here, 231 defects, because Six Sigma methodology nowadays connects everything to defects, not defectives. So, in this case let us assume this is defectives. So, 231 defects over here reported out of 16,000 units like that. So, do we meet the specification? Can we check the sigma levels of this? Okay. And then accordingly we will take the actions like that. So, then the definition is that how do we do that? We calculate defects per unit. Okay. So, 16,000 units and 231 was defects, let us say. So, defects per unit will be 231 by 16,810, that is around 0.0137 like that. Okay. You can go up to 2 place of decimal or 3 place of decimal like that, defects per unit. So, how many defects per unit like that. Okay. When we have done defects per unit, then we can convert into defects per unit per opportunity in 1 units like that. So, one important terminology that comes into over here is opportunity. Okay. So, this term opportunity is explained in any Six Sigma methodology course like that. So, I will only tell that this opportunity has to be defined, and let us assume the opportunity in 1 unit is 1 over here. So, in this case what we are saying is that the defects per opportunity remains same. So, defects per unit is about same fraction, and then divided by 1 also, defects per opportunity also comes out to be same. Okay. So, then defects per million opportunities. So, in 1 unit one opportunity this much. So, in million what will 10 to the power 6 multiplied by 10 to the power 6, simple mathematics over here. So, 10 to the power 6 multiplication over here, defects per million opportunity, this comes around 13.13741 like that. Okay. And now how to convert that into sigma levels? What we have in Excel, this conversion formulas like that, norms inverse, and 1 minus DPO, that values that we have got, and plus 1.5 that is added over here, and that will give you the short term sigma levels like that. So, that will give you the short term sigma level. This function is available in Excel, and you can do that in Excel only. Okay. So, we do not need, but there is a chart conversion what is also possible over here. There is a complete chart where you can find that if DPMO is this much, what is the sigma level like that. So, our case is approximately equals to 13,741. So, let us try to see what is the sigma level 13 how much it is, 13,741 over here. So, if you go over here in this graphically, so what you can see is that this is approximately defects around 13, no. So, this is 13 and what was the value, 741, 13,741, 13,7 approximately over here. So, in between somewhere over here 553 and 907. So, it is approximately near to 3 point, we can say 3.7, so 705 or something like that, we can assume like that. So, is it less than 4? Yes, it is less than 4. So, we have not reached the sigma level which was earlier defined, that customer specification is saying that sigma level for this specific process should be at least equals to 4, and here what we are seeing is that we have not reached that sigma level over here. Okay. So this way also attribute data we can figure out, and using this chart over here, and there are many many of the books will give you this chart of conversion of the sigma level, short term sigma with DPMO. So if you see the last DPMO over here, which is a 6 sigma process, this is around 3.4, that after shifting the distribution this is 3.4, sigma level is 6 over here. So in this case it is a 6 sigma process we can say. So this is a sigma level what we are getting 6, if defect is 3.4, here it is 13.7 something, and in that case it is 3 point something, and that is below 4. So we have not reached that sigma level yet what is required by the customer like that. Okay. So this is all about process capability what we have discussed, and we will now require some amount of statistics which will help us to deal with experimentation. So when we are dealing with experimentation, some basic idea of statistics is required, and I will give you some brief on statistics and some of the things that is really important for design of experiments, and those things I will highlight. Not I will highlight huge statistics over here, but whatever is required at least we should cover over here. Okay, so that I understand basics of hypothesis, although you can do some other courses where basic statistics are covered, and I will give a brief introduction to that, and because that will give some idea what we are doing basic next time. Okay, subsequent lectures over here. So that way we will try to deliver something. Okay, so what is statistics we want to understand, because everywhere there is stat, you see quality over here. So and everywhere one of the values I have mentioned over here, that means basic statistics, x bar I have mentioned, then sigma I have mentioned. So this is coming, what is the estimation of sigma, all these things we have seen, and we have blindly assumed that whatever is told and we are assuming that that is the correct thing, and we will do like that. Okay, but what is the basis of that, what is the foundation of that? So we want to understand that one. So statistics can be divided into two categories over here, and this is all about data science basically. Okay, so over here what we are doing is that we don't have ideas of population. So in that case we need to take samples, because a machine is running for many years, and many samples have gone out. So countably although it is finite, but it is countably infinite basically. So we don't have all information, all data sets over here. So what we do is that we take samples out of that, we take a screenshot, and we say process capability is this much like that. Okay, so how we are making that inference basically, how we are making. So what we do is that we can see statistics in two ways. One is known as descriptive statistics, that means visualization of data what we have told. Then summary statistics, what we have seen, mean, standard deviation, all these locations, and that is one area of statistics which helps us to visualize, which helps us to make some initial interpretation about the data. And the second part of it is known as inferential statistics. In inferential statistics what happens is that we will make conclusions based on the data, the availability, data availability like that. Okay, so decision making happens in inferential statistics, and descriptive statistics shows visualization of the data over here. Okay, and for that, using statistics, it depends on what type of data I am having, like what we are mentioning, attribute data and the continuous data like that. So category of data needs to be identified. So we need to know what are the different types of data categories. So the highest level of data category is ratio scale data or interval data like that. So these are the data which are having the highest level of quality, highest quality level, where we can do many analysis of statistics like that. So interval data means this is the data where we have other than 0 numbers can take any infinite numbers in a scale like that. So, okay. So ratio scale means it includes 0 over here, and then we have ordinal scale where like rating systems, when you go do customer surveys like that. So in that case rate in a scale of 1 to 5, 1 to 7 like that, that is ordinal scale. And there is nominal scale like color, or where we cannot arrange the data into orders like that, but we can say that they are different like that, although ordering is not possible. So ordinal scale ordering is possible, interval ratio possible, but nominal scale like marriage, marital status, or male or female like that. So we cannot say which is bigger than which one like that, which will come first, which will come second. So we cannot order that one. Like colors also we cannot do that. Okay. So most of the analysis what we do in quality is assuming that CTQ is continuous, because we are assuming normal distribution, and for that continuous data assumption is required, or it is interval scale or ratio scale where we are applying this concept of statistics basically. Okay. because we have to make inference after doing experimentation. So, after experimentation we need to let us say select which variable is important, which is not, and which is to be changed, like that. So, that analysis and to make an inference is only possible using statistics like that. Okay. So, statistics, what we are doing basically is that we do not have idea of the population. So, what we are doing is that we are taking samples out of the population like that, and based on the sample information we are making some we are extending our idea about the population basically. Okay. So, we get an estimation from the samples, and based on the estimation what we say is that population parameters will be this much. Like if I get a mean over here, so if I get a mean over here, I want to extend that one, what is the population mean, or where should be the population mean, like that. So, I take only one sample, I cannot do it several times like that. So, with one sample I want to predict what should be the mu values or the population over here. I do not have population information over here. Like in a tree, if you are trying to predict what is the apple weights, like that, and in that case what will happen is that you will take some apples and calculate the weights, and then because this is destructive testing, so I cannot take all apples from the tree, then we cannot those is unnecessary over here. So, we will take some samples, and based on that we will try to estimate about the population over here. So, we will make an estimation about the population. This is what we are doing in inferential statistics. We do not have information of population, that is why we are taking samples, that is why statistics is coming into picture, and we take some samples, and based on that we try to estimate population parameters like that, whether it is standard deviation or whether it is mean, because mean and standard deviation is the only thing about a CTQ we want to infer about. Okay. So, where is the mean? So, where is the standard deviation, or how much is the standard deviation, like that, of the population basically. Have I controlled when I have taken, I have done experimentation, let us say simple experimentation one time, can I infer it in population? So, in population also behavior of the CTQ will be like that. So, what we are doing is that we will do experiments with small samples, and based on that we will try to infer that if I keep this setting over here, it will work for the population, entire population, whatever inputs you are giving, and this is the process setting which we can adopt in future, like that. Okay. So, that is why we are using statistics. We will not do experiment each and every time and then fix the parameters like that. We will freeze it one go, and then maybe after certain time points, if we feel that again experimentation is required, we will do that. Okay. So, what we are doing is that we are talking about population estimation over here, and from sample information that we are getting over here. So, some sample information, and this is the histogram what you see. So, this is the histogram what we are doing over here, and from this information I want to predict about the population. So, some sample information is collected from here, and I want to predict the behavior of the populations, like that. Population can have, normal distribution has two parameters, one is mu and one is sigma over here. So, these are the two parameters that define normal distribution. A complicated probability function which defines the probability density function of normal distribution, but what we are doing over here is that assuming that is known, and in this case I take some sample assuming that is normal, and then can I predict the population parameters, what should be the mu value, what should be the sigma values, like that. Can we do that? So, so that is what we are doing in statistics. Okay. So, from sample information making inference. So, how many ways we can do sampling? There are different ways of doing sampling. When you pick the apples from the tree, how we can do that, and you have a huge target population like that, and from there how to select that one. There are probabilistic way, there are non-probabilistic sampling also methods, that means which does not follow basic randomness in that case, like convenience sampling. Two I have shown over here, convenience sampling and reference sampling, like that. Convenience means based on my convenience I pull any of the people and ask that what do you think about the restaurant food or something like that. I am standing just outside, and whatever customer is coming, and I will do the survey. That is convenience, because convenience means I will stand in one restaurant and try to infer about all restaurants, like that. So, that is not recommended, but that is non-probabilistic sampling. Okay. And there can be referral sampling, that means I am trying to understand the philosophy of criminals. In that case I will ask a criminal and he will give me some other reference of criminals, like that. So, that will be our referral sampling, that means I go from one point, and then the person I am surveying will give me hints who is the next one I can survey like that. So, that is also non probabilistic type of, sometimes it gives you some lead, but that is not probabilistic sampling. There are different methods of probabilistic sampling. One is simple random sampling, stratified sampling, systematic sampling, cluster sampling. So, simple random sampling, what we do generally when we are doing experimentation, and we call it as randomization, Systematic sampling, when we are doing like in control chart processes, what we are doing is systematic sampling. At a given time point we visit the process, and that is assumed to be random. So, the first starting point, and then maybe after half an hour or something like that I am going to the process. So, there is systematic sampling. And stratified sampling, you understand that age group wise I am doing sampling like that. Mostly in survey we use this stratified concept, and cluster sampling like polling and all these things, exit polls or something like that, there you can use cluster sampling like that. So, most relevant to quality over here, simple random sampling and systematic sampling, that is the only thing I can suggest over here, which is of importance to us in this course. Simple random sampling, randomization is, and how do we ensure randomization? We ensure randomization by random number generation like that. So, samples will be selected based on random number. So, if you have let us say 10 samples over here, which one to be selected first? Maybe the first digit, second digit of this number we can take 7, the next one 0 we will skip, then 9 will be taken like that, then 8 will be taken like this. Either I go row wise or I go column wise or row wise like that. Anyway you go, it is basically random sampling that we are doing. So, we select the samples randomly, and we do experimentation. Why we do that? There is a proper reason for that. Okay, why randomization is important like that in experimentation, and simple random sampling is like that, and systematic means which samples I will select, that is random, but what time point I will go. So, at a defined interval we visit the process and take the data set like what we have done in control chart techniques like that. Okay. So, that is systematic sampling. Okay. So, these are the two types of sampling, and what we are doing is that from the samples we are estimating some parameters x bar, let us say average values over here. So, can I extend that, where is the mu values over here, and for that the concept of confidence interval is used. So, that we will discuss in the next session like that. So, here what we are doing is that we are taking some samples, we are estimating some means, and we are trying to define that what is the population parameters like that. What is the population parameters like that. Okay. So, up to this point we will try to extend after this this lecture. After this one we will extend. So, what we have done is that in this complete lectures that we have covered, what we have said is that process capability analysis can have non-normal scenarios. In that case, what can be done is that we can transform the data set is in normality, and then transform the USL LSL like that, and then what we can do is that we can calculate the capabilities, and that is the best way of doing. And but if there is a moderate deviation, in that case we can assume that normality assumptions are we can do that, and without transformation also we can make inference, but plotting the data is always helpful, and seeing that how much skewed it is. Okay, if it is not much skewed, and we do not want to fit another distribution and try to increase the complexity, because shop floor people will not understand so much complexities like that. So, what we do is that in case it is required, we will say process capability is this much, and in case transformation works, we will just show that with this transformation this is the current capability. Do not do it assuming normality over here, because another distribution may be quite correct over here, and this is the non-normal situation. We can address that one using MINITAB, and there is an option in MINITAB. So, we have options over here to fit distribution, and then based on that we can do quality analysis. So, if I go to capability plaque or capability analysis, there will be non-normal scenario, but you have to assign some distribution over here. So, distribution has to be fitted, and based on that specification you give, and it will use some estimation over here for the parameters, and then options will be given, the target same capability benchmark like that. So, I need to fit distributions like that. If I can fit the distribution, perfect distribution, what it follows like that, and it is Q distribution that we are fitting over here. There are different types of distribution, and distributions can be fit and seen which is closest to that in MINITAB also, it is possible, and based on that what we can do is that then we can do capability analysis like that. So, that was the starting point where, and then we went to the discussion that statistics. Then we talked about attribute data and how to calculate sigma labels like that. In case it is defects, in that case how it is done. So many of the scenarios can happen that this is the assembly operations and what is the sigma label of this. So everywhere we want to implement the concept of sigma labels of the process like that. So can I define that one? So I have seen you have seen that DP defects per unit, and based on that we can calculate what is the sigma level of the process. Okay. So then we talked about that whatever we are inferring in quality and all these things is based on statistics, and we want to understand some amount of statistics over here. So that will help us for making inference when we are doing experimentation, basically when we are doing experimentation. And for the basic idea of hypothesis is required, and one of the value that we have used p value, we need to understand what is that p value. So that a brief idea of statistics will help us to introduce in some of the topics which are very relevant to quality, like regression, what will be used, and in design of experiment. So design of experiment is also so how to make inference in design of experiment after doing experimentation, how to make inference, and for that some background is required. So that background I will highlight, but you can always do some course on statistics and to understand more about statistics like that. Okay. So thank you for listening this lecture. We will stop over here and we will continue from here, okay, on statistics, more about statistics. Thank you.